Well, good morning to all of you. In the second class, I introduced to all of you what are the various faults that can be there in a circuit post fabrication. So we discussed that, and it is better that instead of modeling the defects, if we focus on the structural faults, that is stucket faults, bridge faults, right? Those kind of structural faults would be easy for analysis, right? So that, and then in the next class we said that it is not that all the faults which is there in the circuit, if you try to find a test vector to identify those faults, then it will be an enormous task. So what we can do to make the testing more compact, many faults can be collapsed. That means with a single test vector, multiple faults can be detected, right? So our aim is to find out if a particular gate is working fine or not. So we are not really bothered whether among the many faults which is there in the gates, which is the fault. Okay, so even if we collapse the faults, and as far as we are concerned, we are just trying to identify if at all there is an fault in the circuit or it is fault free. Okay, now the next step logically should be, okay, now you have a fault list, and for that particular fault list I have to generate test vectors. So what are the algorithms which we can run? It is not that you pick up a fault list, one fault list, and try to find an algorithm, right, a test vector for that. Then you pick up the second fault and then find the test vector for it. Okay, that is known as an sensitization, propagation, and justification. Okay, but that is a very lengthy process. So there are other algorithms which instead of picking up each fault at one go and then trying to find the corresponding test vectors, there are other methods. We go the other way around. We pick up one test vector and tick, okay, with this test vector these many faults have been identified. So those algorithms will start learning from the next class. Okay, so today what we are going to see is, before that itself we need to do the logic simulation before fabrications, because this data is also important for our testing, right? So what is logic simulation? Like once we have a specification of the system, once it is synthesized, the design is synthesized, you have a net list, right? And from the specification itself, we have, okay, for these kind of inputs, these are the expected outputs, so that is available. Now once you have synthesized the test list, and from the specifications we know, okay, these are the inputs which are there. So a true value simulator does nothing but from the netlist and the input, it generates a set of test cases. Okay, so they are the actual inputs. Okay, you pick up few inputs and you do a simulation, right? And then the computed results are compared with the expected output from the specifications, and if they are not matching, you do the design changes. So you run the loop until you take most of the inputs and make all possible combinations, and you see to it that all of those, for all those input combinations, and the specifications are met. Okay, so this is known as a true value simulator. So this is one of the first step. Once you design the circuit, you got to verify this. Okay, there is no point fabricating a device without running a design verification on that design, right? So this is known as design verification. Now why are we learning this? Because some of the algorithms which we are going to learn in this will be used by the fault simulation algorithms also, right? So that is the reason I decided to cover this first. Okay, now when we do true value simulation, it can be done at a behavioral level also, at C itself, right? And then in that, the timing information, because you have not yet synthesized it. So when you are running this first verification at a high level, so the delays of the gates, the parasitics, those things are not available. But you can still verify whether your design is correct or not functionally. So that needs to be first done at a high level, right? Only then because it is again time these tests will not take much of a time. Okay, if you are running an test at a behavioral level such as C and all, so it will quickly give. So the logical verification, okay, this is a logic simulator. The logical verification can be done without wasting much time. This will run quicker because this doesn't take into consideration right the like the delays, parasitics, okay, capacitances involved in the transistors, or the currents actually available in those transistors and things like that. It will just do it quickly. So this is the first step, right? So if you do this, and then only we move forward. Okay, so the only problem out here is if you do an 100% verification of all the input combinations, then it will take a lot of time. So this is where the test designer have to carefully choose the test vectors so as to minimize the time which is taken for these kind of things. Okay, so as an example, I discussed this in the last class. Suppose I have an 32-bit ripple cadder. If I have to functionally check whether this is working or not, so it is not that 2 to the power of 32, right? Plus 1 carry, so 2 to the power of 33 input combinations are available, actually speaking, but all of them it will be a waste of time if you start doing that. So if you see that this is an this block, they are all the same blocks, the same full adders which has been used. So if I give 0 0 0 0 0 0, so all the inputs as 0, then this will all will become so one condition. So each full adder has got only 3 input vectors. So 2 to the power of 3 is just 8, right? So 8 combinations we have to see, right? But for each of these full adders, right, for the bottommost, the least significant full adder, we do have all the 3 inputs as controllables, right? Whereas these are not C1, C2, the carry is not controllable for us, right? But and hence you have to choose the test vector appropriately so that the next conditions are met. For example, if I have to give a 0 0 1, right? So here if you see here, this is C0, A0, B0, right? So I give 0 0 1. So in B0 1 is to be given. So I can just if I give this 0 0 0 1 and then 0 1 0 1, so all of these full adders will get 0 0 1, right? And next if I give 0 1 0 and 1 0 1, so this is in this order which is written in the top. Okay, so if you analyze that, so you will get in the third case, right, I'm giving 0 0 1, right? So now here if you see here, so these test vectors are all of them are so this carry also needs to be generated. Okay, for example, in this case, right, so 1 0 0 I am applying here, 1 0 0. If I am going to apply that, so here this 1 needs to be generated, so that needs to be taken care of, right? So this is how you just with 8 test vectors, right, I can ensure that the all the full adders are checked, right, for the functionality, because each of them. So this kind of optimization, it may not be possible for all circuits. Okay, this has been made possible because there is modularity here, right? And what is modularity? The same module is repeated n number of times. So these 8 test vectors. So when we talk about, when we subsequently see the optimization of structural faults, then we will see even this 8 is not required, only 7 is required. Okay, so that we'll see later. But for time being, when we are doing logic verification, 8 vectors are required. So irrespective of how many ever bits you have, if you have a 64-bit adder also, in that case also only 8 vectors would be required. So you have to carefully choose these vectors and make use of you have to bring in the required signals in the carry also. Okay, so that way you have to choose. So this can be done. Now this cannot be automated, right? So these kind of optimization right? So here it is what the human intervention comes in, right? So the designer, okay, he can see that this is a modular input, and he can come down with such minimize the requirement of the test vectors. Okay, so this is one thing, and then if I have to find the delays, okay, so the delays is the maximum delay is the carry comes from here, and then it propagates from here to here, here to here, through all these things. Okay, so one is I given 0 0 1 right input to all of them, right, and the next vector, right, should be this 2 followed by 6. Now if you see here, it is 1 0 1, so one carry will be generated from here. If I give one, initially it was all 0 0 0 1, now I am giving 2 ones here, so this carry will be generated. So this carry will come here in this block A11. If you see here, now another one is given here, right? It is 0 1 0 given here. That means one more one is available here. So this carry will come here. Yeah. In the next block also, there's only one coming here. So one more carry is coming here. So this carry will generate it here till here, right? So now first we do this logic verification, and if I have to do the timing verification, right? So if I do the worst case timing verification also, right, at the end of it, okay, I will check all the outputs here. Okay, from here to here, I check all the outputs here, 32 inputs, if it's matching, and then I move this test vector from input test vector from 2 to 6, and within stipulated time I check whether all the inputs are as per the desired thing, right, as per the now what is this output from the flowchart, right? So whatever I have, whether it is matching with the response. Okay, and this is the simulation which is done. So this analysis we need to do, right, if it's matching. Now when we do that, then we can say for sure that this entire circuit, so you don't have to do any timing analysis. This is one, or you can take this option also, 3 followed by 7. So only one of them is a good analysis, right? So both of them also need not be 2 followed by 6 or 3 followed by 7. So total 8 test vectors there and 2 test vectors here will give me this functionality check, and it will say, okay, this is functioning properly. We are not talking about fabrication at all. We are just, as of now, we are talking about the design verification or logic verification, that the desired output is available and it is meeting the timing constraints. Okay, so this is known as design verification. So this needs to be done before we send the chip for fabrication. So these kinds of tests. Right.
Yeah. Can we go to last slide? So here, like vector 1, 2, 3, and 6, 7. So this is like we have to repeat it for all the like address, however we have. I mean, how many bits?
No. Here you're talking about the timing.
Not timing. The pattern. So we have to repeat it for all the like address, right?
No. When I give 0 0 0, right? This is the total. How many inputs are here?
It's for 4.
No, this test vector is not shown here complete.
Yeah. So it will be for like complete 32 bits, right?
Yes,
here?
For complete 32 bits.
Right? But for fourth and fifth case, it's like FA0, FA2, FA1, FA3. And then we have to repeat it like same for the last one.
Which one?
For the test vector 4th and 5th. So it's specifically mentioned that for FA0 and FA2 we have to apply 0 1 1, and for FA1 and FA3 we have to apply 1 0 0. So we have to repeat this pattern like
yes,
till
we have
like
to repeat, so that the carry, so that each these adders, okay, they are applied with this.
Okay,
right?
Okay.
For different combination. So this test vector, this here, all the 32 is not shown out here.
Okay.
Okay, all 32 is not shown. Right. So this is like ultimately once that once we do all these things, okay. Now I have a verified design after that, right? Okay. Now the verified design is available. Verified input simulation is available. So there is a lot of test vectors. This has come from my previous from this. Okay. Once having done that, okay, I have an verification, right? Then this netlist I am going to give it in the fault simulator. In the fault simulator, okay, I will have now a lot of the fault list will be up there. Okay, now insert all the fault list. Now from the fault list, I am going to do an I am going to apply a test vector, say one test vector. I am going to apply say one test vector. It will tick off many faults, right? So that will compact my test. Okay, so there will be some redundant test vectors which you might have used in the logical simulation. So all those test vectors, redundant test vectors, will be removed. And as and when one test vector, many faults will be detected in one go. So keep removing them from the fault list. Okay, because okay now, slowly when you run this, and your entire fault coverage should be done, and once that is done, you as and one right one test vector, a combination of one test vector clears a set of faults, so that will keep moving to the test generator. In the test generator, okay, you'll keep having a list. Okay, this is the test vector, and these are the faults now with this. Okay, done. Now I take the next test vector, right? So once it is done, here the fault list will keep reducing, because that you have moved it already into the test generator and register, right list. Similarly, if you keep doing that until all the fault are being covered and the corresponding test vectors are available. So finally, when we run the fault simulation simulator, all the faults should be there, and a corresponding test vector should be there, right? So there could be one test vector which is covering several faults also, and that is what optimization we have to do, right? So now coming back to simulation of the circuit. Okay. Now,
Sir, just one
yeah.
question on the previous slide. So this is happening at the testing level or verification?
No,
Trying to understand.
no. This is
Yeah.
going to happen in the testing, which we will go in the next class, right? I just
Okay.
said
So these.
here this which is written in the shaded portion. This is what we are doing right now,
Okay.
right?
Okay.
This is what we, because this is required, right? So this which is a shaded thing which we are going to cover today, and this we are going to take. So there are we also have, now we have an this we are going to learn today. We already have an collapsed fault list, right, from the first two classes, right? We know the fault list also, right? So I can say that this fault list of fault list is also available with me, right? Now we are going to cover these, and then the next blocks we will see in the next class. Okay.
So this is in a tool, or we have to manually confirm this faults and keep track of them. How does it work in the industry?
Which one?
The fault stimulator, like is it on a
No.
Linux
It's
system
on an
or
tool only. We'll see various
okay,
algorithms
okay, fine,
which will
okay.
optimize this, right? There's several algorithms which will optimize this. Okay. Now you can, once you design an circuit, right? Any circuit at the functional level, we can design it like this, right? Suppose a half adder at a functional or behavioral level, I can write a code like this, like module half adder. A and input is A, B, output is C and S, and I can just tell assign S is equal to A. This is the symbol for in Verilog for XOR, and assign C is equal to A and B in Verilog. Okay, so you will have to learn a little bit of Verilog probably for your assignment. Okay, so this is the small program written, right? It is in the behavioral level to implement a half adder. So when I am writing in the behavioral level, I am not even bothered how it is going to be synthesized. Okay. Or what are the gates and things like that. Okay, so that is for the tool to decide. Okay, what kind of gates it will put, right? Whether it is going to implement with NAND, NOR, or XOR, or AND, whatever it is. So when I'm writing, first the circuits have to be modeled, right? So I can model the circuit at this level itself. Okay, or I can go one level deeper, right? These are the various model, right? You go step by step. Once then I can do it at gate level modeling or logic, where I will specify the gates which are there. Like again for this simple circuit, if like I specify, okay, this is the inputs A, B, C. This is the output. Okay, in between the interconnection, and this is not available as an input or an output, right? So that I declare as a wire, right? And then I write and, okay, and means an AND gate, right? G1. So all there will be several gates in the circuit. So each of them need to be given some unique name. Okay, so this is the syntax in Verilog. So there is a one gate, okay, whose output is W1. So this is output and these are the inputs. So this is the syntax in Verilog. Okay, so AB. So that means wire 1 will have an AND of A or and wire here G2. Now G2 I have to specify these. If I write G here, no, there will be a syntax error. I have to write give different names to each of the gates. So G2 YC. Okay, now Y is an output out here, right? So I don't have to put an intermediate wire here. So now when we are doing at this particular level, all these wires are the same, they are interconnected only. So Y and C, and then this is again an OR gate. OR gate, output is Y and input is Y1 and C. So this is known as here we are not bothered about what the tool is going to synthesize the gates. Here we are telling, okay, these are the gates which I want. Okay, so specifically this is modeling at the gate level.
These are gates and that case sensitive, sir. Letters are case sensitive. Letters are case sensitive. Means
here, yes.
Capital A and
yes, letters are case sensitive.
Sir, is the gate level modeling automatically generated by tool, or we have to program it?
No, we see we can the like the tools like Xilinx, you can write a behavioral also, right? And if you do the behavioral and you can synthesize it. Once you synthesize it, it will generate the gates. Okay. Now while synthesizing, the tool would ask you to know what is your optimization goals, power or right, delay, correct, and area. So those optimizations you have to take. So depending on that, it will synthesize an set of gates, right? So but when you are doing a gate level modeling, you are picking up the gates itself, right? Here only optimization you can do is, again you can do here also you can set the goals for power and all, right? Here when you do for power, and if your goal is power, then in the library there could be an and which is low and low power or high or fast power. So it might pick up those gates, right? Whereas if you are giving this, okay, if there is a possibility of designing the circuit in a different using a different topology itself to meet your goals, the tool will pick up that particular circuit also, right? Suppose this is AND, right? If you see, suppose this is an AND of 4, right? In this particular configuration, okay, the delay will be more, right? But there could be more power, because the switchings involved will be higher than implementing it like this. Right. So in the functional level, I just say, okay, y is equal to a b c d, right, in the behavioral model. So the tool can implement it like this, or it can implement both of them of same, right? So if you have set propagation delay as your goal, it might implement it like this. If you are set your goal as low power, it might implement it like this. Okay. Now because here also, like suppose this is gotten very less activity. It is remains most of the time. Suppose this remains most of the time 0, right? This is 1, right? So there won't be many activities here, right? So so this has got a lesser switching activity. So we'll see these examples in our advanced VLSI course. So this will have slightly lesser power than this particular topology, right? So this is just an example. What I mean to say is, when we give a behavioral function and ask the tool to synthesize gates, so you have an option to select, okay, high power, or the goals, to set the goals. So accordingly it will make circuits. Okay. So whereas here also optimization is possible, right? Because if you see the actual tools, if you have got components, if you from the Fab Lab will give you different types of AND gates also, right? Slow AND gates, fast AND gates, right? Depending on the with high power and obviously speed will be when this it's operating at a higher speed. That means it will have more current carrying capacity, and higher current and dissipation will be there. So that kind of thing shall be there.
So does the way we test get affected by what level of modeling we are on? Like, does behavior versus gate level we change our approach, or like what is the significance of looking at this different models at this point?
Yes, it is going to make a difference. I'll give you one example for that. Okay. So so we have to understand that when we do this, okay, there is a possibility that we miss out some aspects. When we go here, we'll cover more faulty aspects. When we do this, further more things will be faulty aspects will get reflected. I'll give you one example, and then it will be clear. Okay, at the switch level simulation. Okay, now what happens is that each of these transistors are modeled as a switch. Okay, that is nothing, no current or nothing. Okay, it is just a logical switch which is used. Okay, either it is on or is it off. Okay, so that is known as switch level modification. Then I could model it at a circuit level, right? In the circuit level, apart from that, some electrical elements such as resistors, capacitors, and inductors are also used. Okay, and the final the most detailed simulation would be timing level, where a transistor is modeled right, using whatever BSIM3 model or whatever it is, in which the parasitic capacitances and everything is taken into consideration. So as we move from the top to bottom, the amount of time which will take for logic verification will increase, right? So if I use this model, the time required will increase. Okay, here it will do a quick simulation and tell me if I am going to do a simulation here, but this will take into consideration the timing aspect also. So I would rather start first here, right, and see whether the output is available or not. Okay, either I do here and then slowly move down and try to find the issues. So because no point doing a transistor level in the beginning itself, right? So because here the failure could be because of the sizing of the transistors also. right? Here, but that it will not take into consideration at all. So this, first you do this and clear your test run, and then if you find this is working fine, and then only we move bottom, right? So and then once why gate level simulation will when we are doing incorporating the, if you remember from the first class, when we are incorporating the DFT, right, designed for testing, then you want to observe the output values also, right, in between, and so gate level modeling would be helpful in that particular case. Now this is one example why circuit level modeling is important. Okay, so this is an transistor implementation of an MUX. Okay, so there is one function here, and there is another function here. Okay, and this is a MUX which will select only one of the outputs. Okay, here, right? When I do the gate level modeling, and or if I tell the tool to implement it, okay, the tool can implement it in this way also, right? The same functional. If I give an gate right, ask the tool to implement it, it can implement whatever the MUX like this. Okay, now how is it working like a MUX? See, this is an NAND gate, this is an NOR gate. Okay, so there is no problem with that, right? And this is the like if I write an functional line for MUX, it could get implemented here, right? Where I give an if I give 1 here and 0 here, okay, what will flow to the output? This will get, right? And if I give 0 here and 1 here, this will flow, correct? So if I say right, and for this is the control bits, right? 2 control bits, right? This and this, right? So I say for control bit, okay, this control bit for the MUX control bit, if it is an 0, right, I enable this gate. If it is 1, you enable this gate, right? So it might implement that function, and it might do like this. But the problem is, okay, when I am doing an testing, right, when I am doing an testing, I would also want to see, say, what happens if the both of them for say, because these are also coming from some other circuit, right? So also I have to take care that for some reason, if both of them come as 1, right? So what would happen? Okay, will this entire circuit burn off or not? Right? So some safety features needs to be incorporated, right? Because this is also being synthesized from somewhere. Now in this, when I do a transistor level simulation, if this is 1 and this is 1, and for this particular input combination, this is a 1 here, this is a 0 here. So right, so this current can flow from here like this, right? This is on and this is on. So there could be a direct path between VDD and ground. Okay, so these kind of issues can only be detected, right? Because this could be stuck at one fault, right? Where I'm doing a fault simulation. So these kind of things can at a transistor level, when we do it can because while fabricating this can happen, right? So that is why the reason when we do logic simulation, we take into care, although we say only one of them should be 1, but we also take a condition that both of them, suppose if it is 1, is the circuit safe for operation? But here we find that it is not safe for operation if we design it. But when I go, if I ask the tool to make synthesize this using at gate level, then here if I give 1 1 also, nothing would happen, right? So this is 1, this is 1, this is an OR gate. So the same MUX implemented with the gates, okay, I'll get some output, and this will it is going to give me some faulty output, okay, but then this is not going to show the actual scenario which is going to happen, Okay, so we miss out on that information. So we start with this. Okay, this we start with asking the gate tool to do this, because it will take lesser time and we do the functional check. But before fab, you need to do the transistor level simulation also, right? All the fab lab will tell all these things. Okay, the delays also. So so the delay aspect also can be incorporated during here. But ultimately, finally, right, you need to do a transistor level, this level modeling, right, before we send to the fab lab. So this is an important run. It is a time consuming run, but this needs to be done at the last. Okay, because after doing the transistor thing also, you will do a layout, and also all those delays, parasitic delays also will get incorporated. So that final run at the transistor level is also important. Okay, so does that answer your query? Why do we have these different kinds of levels of testing? It is time versus accuracy. Okay, so we start with the easiest one, keep testing, because the result of suppose there is a 1000 transistor in a circuit, once you do a transistor level simulation, the result could be available only after a week or so, right? So and then if there is a problem, you go and again change something, and then again you wait for a week. So it is going to be waste of time. So it is better first you check the functionality at a higher level. If it is working fine, then only we move to the higher levels. Okay. Now most of the tools, right, also takes X as an input. Okay, you may not have defined the input at all, right? So in a circuit, you have made a circuit, you have not defined X, it is unknown, right? So you have made a circuit, you have somehow that input is not defined, right? But what happens then? Should this simulator stop there, or it should run, right? So that can happen, right? So when you're programming, it is possible that that input is not there. So most of the modern day circuit simulators, they take X also as an input, as one of the inputs. Okay, now if you see here, also it takes Z also as an input. Okay, Z stands for high impedance, and X stands for unknown. Okay, unknown means it's not able to compute that, right? So now if you say for an AND, 0 0 is 0, for an OR and for a NOT, 0 1 for a AND is 0, for a OR is 1 here. Now 0 and the other input is not unknown. Okay, it is X, right? For a AND it will be 0, because one input is 0. So irrespective of what is there, and it will be 0. For an OR, okay, because now the output I can't for sure say it will be 0 or 1, because the second one is 0. Okay, that is okay, but this is X, right? So the output also is X. So this is all right, the truth table of the gates. Okay, now the gate has got three kinds of inputs. Now instead of an Boolean algebra, I am speaking about some other algebra which has got another. Okay, instead of a binary logic, I am now talking about three states here. One more variable has been incorporated. Okay, so 1 0 is not an issue. 0 1 0, 1 1 is not an issue. Now 1 X, right, for an AND gate. Now this is again, it is not known, right? So the output could be 0 or 1 depending on the value of X. So I write an X out here. So X 0 is 0, right? Now X doesn't mean, okay, this X and this X is same. Okay, that is important. Okay, X just means it is I don't have an X and X bar. Okay, it's not like that. To give a simple example, like I say, input is X for an inverter. Okay, output is also X. That means it is unknown. Input is unknown. Output is unknown. Okay, it is not that it is x and x bar. Okay, we don't have that kind of so these simulators, they don't take x and x bar. Okay, is this point understood, right? X means it is unknown, it is just unknown. Okay, so there is nothing known as x bar out here. So this is the truth table. Now,
sir, can I go in back slide? In that, not have only one input.
yes.
So that is your problem. But and or that it depend on x. Output is depend on x. I mean, whatever x will be there, that will be output only.
Yes.
But not only have problem, sir. Not having only one input.
No, it could be for an XOR gate also. There could be a problem, right? Suppose I have a 1, right? I have an x. If it is 1 here, I'll get x bar here. If it is 0, I get x, right? But that is not taken into consideration. Simple. It just says x. It will throw the value output as x.
Okay, sir.
Okay, so that's how these simulators work. Okay. Okay. Now, suppose I have to realize this function. If I write a program like this, is there any error you could see here? I have taken A, B, C, D, right? Output is Z, and I have taken 3 wires. The first gate is an AND gate AB. Second gate is a CD, okay, and the third gate is the output gate, right? Here, if you see here, if I have to implement ABCD, I should have given W2, right? But I have given W3. So this is actually as far as the tool is considered, this is a high impedance input. It is hanging input. Okay. So if I do a synthesis, okay, in Xilinx, okay, so I get like this, right? AB, there is an AND. BC, there is an AND. This is a third AND. So this is taken out here. This should have been coming here. Okay, but that is not coming because I have given W3. So this W3 is come here. So this will get synthesized like this. Okay, it will not, the tool will not show any error, right? That this is not available and all. Because if you start throwing errors like this, right, you won't move the program at all. So it will run the program and accordingly it will do the synthesis. It is for you to analyze that, right? And then I give 2 test conditions. One is 0, 0, 0, 0. So the output is expected to be 0. And then I give one more condition, 1, 1, 1, 1, right? And I do. So if I do the simulation, so this is what I am going to get at the output, right? So if you see here, this is the W3. It is high impedance throughout. So it is indicated in blue, right? So when I am giving all zeros, okay, the output is 0. Why is it 0? So if you see here, this is an AND gate. One input is 0, right? So irrespective of whether this is whatever it is, Z or something, this will throw a 0 output. So there is no issue with the 0 here, right? But whereas when I am giving a 1, 1, 1, 1 here, so I am getting a 1 here, whereas I am getting an high impedance from here. So now this gate doesn't know what to do with the output. Okay, what would be the output? In that case, it is showing as X out here, right? So input is high impedance, output is X. Okay, so it will throw up an this thing, right? So now once you get your simulation results like this, you have to go back and analyze why this is happening like this. Okay, so once you run the code, if you are giving some test vectors, and if you are getting some output like this, so then you go back and analyze the thing. Otherwise, all these tools will take these also as inputs, and these are also available as output. Right now, I take an same example. So AB or CD. Okay. So now here in the OR gate, okay. So this is the input which I have given here. So in this case, when I give the test vector, same test vector I am giving. First all zeros and then all ones. So here, if you see here, during the first run, I get an X output. Okay, because in the first run all zeros are given here, right? So I have a 0 coming to this OR gate. So whereas the other input is Z, which is not known, right? So this will throw up an error. Whereas in the second run, when all is 1, I am getting a 1 here. I am already getting a 1 here. So this will give me a 1 irrespective of what is coming from here. So in the second run, there is no issue. So in the second run, there is no issue. Okay. So this is in Xilinx, everything is done. So I did this just to show these things, okay, how these logic simulators work. Okay. Now we can make an module and a mux module. Okay. Also, if we just write this, okay, this is how it will get implemented. Input is a select line, and then there are input 2 data lines, and there is single output. Now I can say assign y is equal to based on select. Okay, when I write like this, it means if select is in 1, then I1 okay will be assigned to y, and if select is 0, this will be assigned. Okay, so this is the syntax in Verilog. Okay, understood, right? How does this work? This function. I am writing y is equal to select, and then I put a question mark. Okay, when I write like this, then I need to specify 2 more things. Okay, that means what to do if select is 0 and what to do if select is 1. If select is 1 true, then this y will be assigned I1, and if select is 0, I0 will be assigned. So I0 will be routed towards the output if select line is 0, and I1 will be routed here. So if you do a simulation, you will get a proper result. Doesn't matter. Now you could also have tri-state buffers. Okay, all these simulators will take tri-state buffers also, because these days we do have a lot of tri-state buffers also in the designs, like especially during when we have designing circuits with past ancestors. Okay, we have all these tri-state buffers coming in, right? So here if you see the it is assign y enable. So when the enable is 1, y will be assigned x, or if the enable is 0, then it will be at an high impedance state. So this is the format for high impedance. Okay, dash b, it means it's a single bit, and then z means it is high impedance. Okay, so so this is how an tri-state buffer program can be written here. Now this is like I have two tri-state buffers. I can use it to make a mux. Okay, now I give this control signal here, right? I give a control signal here, right? And then I tell, okay, I am activating both the tri-state buffers, and one of them will be activated at any given time, right? So so it will so if I tell so either this will be routed, or this will be routed here. So this is an mux, right? So this is the control signal which is there, right? If this control signal is high, this will be activated. If this control signal is high, this will be activated, right? But suppose if both the tri-states are activated, and one input is 1 and the other input is 0, right? Even this simulator at the output, right? At the out, if this tri-state buffer is implemented in this manner, and I have a clash of 1 and 0 coming here, okay, the simulator will throw an unknown output. Okay, because if 1 is coming from here and a 0 is coming from this path, because both of them have been given. So here if you see here, the control signals both are high, both the control signals are high, whereas the input signal out here is 0, here it is 1. So I have a 0 coming here and I have a 1 coming from here, right? So there will be a clash. So the simulator will say, okay, it is an there is an issue with here. So now this is possible. Why this has been possible? Because this mux you have designed in this manner, but if the same mux gets designed in this manner, here like this, right, then that that fault cannot be detected, right. But if the fault is, but if you have designed it in this manner, right, if you are using a tri-state buffer, and so it all depends, right, how the so if you do a detailed design, if you don't at the gate level, more often than not, you will be able to detect such faults, right. If you do a behavioral level modeling, then many faults may get undetected. Okay, so that is the reason when we do we have to not just do a behavioral model and assume that our circuit will function without fault. Okay, so you have to do a detailed verification also, right. Now if you see each of these gates, right, so I have the actual model used by these simulators is not binary, whereas it has got all the inputs, right, 1 0 z and x. Okay, 1 x z, and for an AND gate, if you see here, the output is 0 1 and unknown. Okay, now if you see AND is 0, one input is 0, all of them will be 0, one input is 1. So 0 1, 0 will give 0, 1 will get 1. If it is high impedance, it will get x. If it is not known also, it will give x, right, because this is there is a difference between z and x. Okay, z is an high impedance node, x is an unknown. Okay, we don't know what is there, right. So because here, like for example, let me explain the difference between here this is z, right, but this can this output can probably drive another gate also, right. So when this is going to the another gate, at that time it will not be z, it is x, right, because this is the output of a logical gate, and it can be either 0 1 or x only, because this output, okay, there is no z which will come out of here. Here it is z because it is high impedance, it is not been defined at all, it is left open. So this is z, whereas the output of this particular OR gate, right, here it can be z, and the output at this level, it can be either be 0 depending on the input combination, 0 or x. Okay, so when this is going to another gate, so for so for each gate, so the outputs will always be 0 1 or x. Okay, so unless it is an, if it is a tri-state buffer, in the tri-state buffer the output could be z. So these are the model, how do we model these gates. So so for 1 it is 0 0, 1 0 is 0, 1 1 is 1, 1 into z, 1 and z will give me x. Okay, 1 and x also will give me x, right, and similarly if here it is z, right, and 1 is 0. So if it is 0, all the output will be 0 here, and for 1 here if it is z and x, and it is going to give me x, right, and it is z out here and it is z out here, then it is x, x also will give me x. So these are the two there. Similarly for an OR, if you see one of the inputs is 1, then everything will be 1. If 1 is 0, then it depends on right, like for 0 it will be 0, 1 it will be 1, and for z and x it will be x, right. So all these simulators now will now take all these variables into consideration. Okay. Now this is for XOR and XNOR. Okay, so you could verify this. I'll share this PDF. So this is the way the actual truth table of an XOR and an XNOR looks like.
Sir, I have a doubt.
Yeah, tell me.
In last slides, when input is Z, why output is X, not Z? Like in AND OR?
See, output is not known. right? So Z is an high impedance. High impedance means it is not connected to ground or not connected to right VDD,
Yeah.
right? Whereas X means it is it is not known. It could be 1 or it could be 0, right?
Sir,
So if you see the
like in
transistor implementation, right? Right?
Okay.
If I have an sorry, right? If I have like this, right, some gate, okay, NOR gate, for example, right? So even if this is left open, right? This is like applying a 0, right? Here it will never go to Z.
Okay.
Correct. Now you might want to think that this is open, right? So can I take all Z input as 0, right? So that is actually not done because leaving this open for this particular circuit it might appear it is 0, right? That may not be the case always, right? Like for example, for a TTL gate family, right? And open is actually 1, indicates 1, right?
Okay.
For a CMOS logic, open is 0, right? So for various circuits, Z may appear at the input as 0 or 1, okay? So and that is the reason, but whereas the output, okay, unless we are not talking here about faults, we are talking about the final output. Here it is expected that this output will either be connected to 0 or 1. It will never be this is a static logic, and hence we model these gates as the output as X. Is it okay?
Okay, sir.
Okay. Anyway, thank you for bringing out that point. There is an when we do the simulation and we do a testing, this is an X. Okay, X is not Z. Okay, there is a difference between X and X means we don't know. X can have only two values, 0 or 1. Which is that? That is not. Okay, it is not Z. Okay, so suppose X is coming from a previous circuit out here. When I do a simulation, okay, this will give me X here. This will give me an X here, and the simulator will say the output is 1. But if I'm practically doing post fabrication testing, okay, in a circuit like this, I can say F will always be 0, right? Because if it is a 0 coming here, for example, okay, so I'll have an 0 here, 1 here, this will give me 1, this will give me I am making some mistake. XOR of this will be 1, right? Always. Sorry.
Yes, sir.
This will be 1. Okay, I have made a mistake here. So this will be 1 here, right? So if this is 1 here, it will be 1 here, 0 here. This will be 1 here, right? So but you see there is a small dichotomy here. So in simulation, when we do all these things, okay, X. Here when we are doing testing, okay, we might get a 1. So this is a small issue. Okay, so while we do the simulation, obviously we have to take care of all these things and kill those issues. Okay, because in testing again, if you if this is skipped in this here, then it might get caught here like this. Okay, so and here we may not be able to diagnose what is the problem, right? Because we don't have observability also at these nodes, right? So we won't come to know what is the issue here. So these kind of issues needs to be first resolved at the simulation level itself. So if these things gets passed through and it comes to the testing phase, then it will be almost impossible to identify why this fault is coming here. So now when we design circuits, when from your VLSI days classes, you might remember we restricted the fan out to 4 actually, right? If you fan in, if you stack more than 4 transistors, we told that and it is going to increase the delays and things like that. But from the testing point of view, okay, we generally restrict it into 2, because it is like, each of these are actually we can assign 4 different values, right? 0, 1, x and z, right? Now if you see here, so those many combinations, right? So the truth table of this itself will get very complex, right? So it is better to have 2 input gates, and you have for testability. This we learnt a little bit during our VLSI days, when we capture the output through flops in between, right? So this kind of 2 inputs, and so that is the reason for most of the gates are restricted to 2 inputs itself, because you now have to cater for x and z also, right? So those many input combinations are there. Now when we talk about the transistor level modeling, right? From the here also there are several methods, okay, when we model the delay, right? Because all these capacitances will come, and finally there will be. So before going to the transistor level modeling, right, this is our actual transistor, right? The currents are varying, the capacitances are varying at each nodes, okay? So delays are there. So the output need not be like this, and there could be charging and discharging times involved. So before going to transistor level modeling, at the gate level itself, certain delays can be introduced, okay? So that is when we talked about different kinds of models, right? Here, right? Here, right? In when we are doing, we have not sorry. In the gate level itself, when we do, right, when we do we can do a timing analysis at the gate level itself. If we model this timing also into the gate, right? So this is possible. Like first we run a Verilog code, and we do a logical verification, and then we do the synthesis, okay? When we do the synthesis, the actual library, from the library these gates will be picked up. So there are several delay models available in the library. So you can choose one of those delay models, okay? So you can do a timing analysis at the gate level also, okay? That is what is done in the industry today. Rather than reaching although finally transistor level modeling will be done, but the timing analysis can be done at the gate level also, right? So now for that there are several models available to do timing analysis at gate level, okay? So the first model is a zero delay model, in which there is no delay, okay? Zero delay. So this is the A input. This is the kind of an output for an inverter, okay? Now the second is a unit delay model, okay? What we can do is we can say that, okay, this has got an definite some unit, okay, a few picoseconds, it could be something you define that unit delay, and you say, okay, this much unit delay will be there. So this shaded portion, starting of the portion, is where the input is changing, okay, here, right? And this is where the output is changing actually, right? So you have a unit delay model, right? Or you could have multiple delay models, right? So multiple delay models is like for each gate, okay, there could be appropriate rise time and fall time, different fall times you can specify. Now for in this particular case, right, if the input is switching, right, and not, if adequate time is not given, it is possible that when you do a simulation, it was trying to come here, and then meanwhile, okay, the output has changed. So you can see all these kind of errors also, which are coming up the moment you introduce the multiple delay. So you have to take care of that. So you have to give adequate time for the outputs to signal, okay, for the signals to stabilize, okay, and then you could have a max and minimum delay. For each gate, you can specify this is the minimum delay and this is the maximum delay. Okay, so for a particular condition, like when we do ST analysis in our advanced VLSI class, so each gate we will see that it is defined by a max delay or minimum delay. It will be specified. So whether to take max or minimum, that depends on the analysis which we do. We'll pick up the worst case. Okay, in some cases, and minimum delay is the worst case. In some cases, max will be the because minimum will cause a hold problem in the hold types, and max will cause problems in the setup time. So when we are doing generally setup time, we'll pick up the max delays, and when we are doing the hold analysis, we will do the minimum. So this when we do the gate level modeling, before coming to the transistor level, in the gate level itself, timing analysis also can be done, and depending on the model which has been provided by the fab lab, right? Okay. So now we have a circuit out here, right? Now what we have to find whether this logically this is working or not. So after having designed the circuit, so okay, the first step would be to levelize the circuit, okay, and make a compact code for it. Okay, it is known as compiled. So what is levelization, and I will talk about that. And once I have a compact circuit or a compiled code, then each data, okay, input data, I will take it as a variable, and then for each then I will take it as a variable. I will keep changing the variable. Okay, so initially I will take 0 0 0, right, and I will run this code completely, and I will see the like for each input vector I set a primary input variable, and I run this code, and I get the final answer. And that final answer I will verify with my specifications. Is it meeting? Suppose I am giving 0 0 0 plus 0 0 0 0 1. The final, is it true or not? I will check that. Once it is done, I will change the primary input. Again, I will run this code. So multiple times I will run the code. So first I have to compact the code. Then I have to initialize the variables, okay, to some value, right? Run the code, find the result, right? And if it is matching, and also I will have to keep saving that, because finally that data is required for my testing purpose. Okay, when I am designing my test algorithm, I will require that data, that for this set of input functions, as per specifications, okay, this is the expected output. So this table also needs to be generated. So this is what a true value simulation does. Okay. So first is circuit simple. So several steps are there. Circuit simplification, then circuit levelization. Okay, I'll explain these two again. And signals are treated as variables in the code. Okay, so you assign values to these codes. Okay, now here, okay, when we do this, when the code simplification, okay, we are not going to consider x and z values. Okay, this particular algorithm runs fine for 0 1 only, right? And timing is also not modeled. Okay, so this is one of the very first run in the initial stage. Okay, after that only we'll go for timing. So timing is not considered, and x and z is not considered here at this time. So first is circuit simplification, and because once you have written the code, there could be once you have written a code, you have to see that unnecessarily you have not complicated the circuits. Okay, like these. Right? Some examples are given here. Suppose an A is given here, there is an AND here. Okay, so this is actually equivalent to an inverter, right? A chain of inverter. While in like this may be required subsequently for timing analysis and all, where you want to intentionally insert a chain of inverters for tackling the delay aspects, right? But when you are doing a compiled code simulation, this will unnecessarily delay the process. Now you have to understand that when you are doing compiled code simulation, okay, you are giving lot of test vectors and it is a time consuming process, right? So although this may be actually required in the final circuit, right, but before running at this stage, at the initial stage, okay, since I am not doing a timing analysis, now all these things can be simplified, right? So there is a buffer. This buffer may be required finally because there might be a current carrying requirement. But in compiled code simulation, I am not bothered about the timing itself. So why to keep this buffer in between and delay the entire process? So I don't do this. So these kind of this is known as circuit simplification. So this needs to be taken care of initially itself, right? So after that, once you have done the simplification, you have to check for levelization also, right? Now suppose this is a full adder. Now I am not doing a gate level modulation. Okay, compiled code simulation generally runs in C only. Now this is an actual program which I ran online. Now if you see here, the program which I wrote here is sum is, okay, so the input is A, B and C, right? And this is okay, they are integers. Sum is carry in this gate, okay, carry in XOR of P, okay, and then I have defined a P as a XOR of A and B. I have defined sum, I have defined a P, and carry I have defined as A and B or B and C or C and C. So that also I have defined. And if I run a program and I give an input 101, okay, will it give me a correct result?
No.
Why?
So P should have been defined before some, right?
Yes. So when I do a compiled code simulation, okay, it will go line by line. Okay. So now here P is defined later on and sum is defined first. Okay. So if I run a simulation, so it shows me like right 101 sum should have been 0, right? But what has happened here is the sum has got computed first, so it has taken this as a 0 and it has computed, right? Whereas this was assigned as a 1 later on here, right? So that becomes, so this is known as levelization. Okay, so you have to ensure that okay, all this code whatever is written for your logic circuit, they occur at the same order, because in which it needs to be computed mathematically, right, step by step, right? The code runs line by line, right? So that is an issue. So now if I swap these two inputs, I'll get the correct answer, right? But when I do at gate level modeling, when I do that, right, the simulator this is a Xilinx simulator. If you do that, there is no issues here, because it will take the timing and things like that, and then right, it will give the correct answer right here. But when you are doing it at a high level, like a C program, to verify your design initially, which you should do, right? So to save time. So when you do that, in that process, you have to be careful about the levelization aspect also, right? So what is the compile code simulation does is, it just gives vectors a parallel each of them. Okay, first it optimizes, right? Optimization is nothing but simplification, then levelization, then the codes are generated. Okay, the advantages and then the outputs are monitored, and it is a file is made for the fault test bench. Okay, for the next step. So this is what it does, and the answers are verified from the original specs. Okay, so this is it can run parallelly, right? The problems with this, we will see that the problem is, every time a new code is given, it will run the entire code, right? First I give this input A, B, C, Okay, for next test vector, I will give as say 1 1 1. Then it will start from here. From this entire code is run once every time a new test vector is given. So that is the main disadvantage of this. It is time consuming. Okay, every time a new test vector is given, it will start from the line 1 and it will run the entire code. Okay, so that is the drawback of that. So we can have something known as event driven, which is much faster than the code compiler, right? So this is much faster, event driven. Okay, so within the event driven, I can have zero delay model, nominal delay model, and a data structure model. These are the three different models which are available within the event driven. So in the event driven, okay, first one simulation is run, and next you give a next test vector. It is not going to again start from the code. So it will see, okay, where all those new test vectors, which part of the circuit the data needs to be changed. So it will change only that particular. It will retain the previous value and just keep changing the new in the paths where the new input is likely to cause an output swing. So it will keep doing calculations only in those paths. Okay, that way you will save a lot of time. Okay, so that is known as event driven. So so we will see that when we try to automate the faults, where most of the things will work on event driven. Okay, so the same logic we will be using it in our test pattern generation, also event driven simulation logic. Okay, now suppose you take this particular circuit. Okay, suppose I have initially 0 0 0 0. Okay, I have already computed. This is the first initial vector. I have computed these values. Okay, now I am just changing this last value. Okay, here D, right? So do I have to change here x1 again? I don't have to compute x1 again once again, right? I don't have to compute x2 again, right? I just have to compute x3, right? Obviously now in this particular case, okay, now x3 may or may not change, but since the input has changed, okay, I will say let me compute the output of G3 once again as per the new truth table input combination. Initially it was 0 0, now it is now 0 1. So but for this it is 0 0 and 0 0. So this input D, so each gate will be mapped to its input, and if there is a change in the input, then the output will be computed once again. Okay, so although we can say, okay, since it's a 0, x need not be computed. Okay, that is not the way it is done, right? If one of the inputs is changed, it will refer back to the truth table of this particular gate. So x may or may not change. Okay, now if this is not changing, then I may not bother about G5 at all, correct? So I'll say, okay, there is no change in x, and so G5 also need not be done, right? So that is how this moves. So I'll give an example, so then things will be even more clear. So this is what it is done here, event driven. This is the same thing what I explained. I think through a few examples I'll make it clear, this flow chart. Now suppose this is an so you have an this works in an for each gate. Okay, the inputs would be known, okay, from the net list, and also you will create an FIFO. FIFO is first in first out. Okay, queue for gates. Okay, now I am changing these two inputs simultaneously, A 0 to 1, B 0 to 1. Okay, so in the FIFO I push in two, like in this particular case I have inputs also I have taken an B as a first and then A. So in the FIFO I will register, I will put these two gates G1 and G2, okay, because these gates are going to get affected. So I'll keep doing this until I get an 0 in this FIFO. Now I have put two gates here. Now in the next what I will do, I will get one of the gates here, okay, first in first out G1, and is G1 going to then I will compute the output, right? Is there a change in output here? If G1, okay, sorry, G1, is there a change in output? Anybody here?
No.
No,
No,
right?
no, sir.
So should I push G3 here? No, right? In this column I will not push G3 because G1 making a change doesn't affect, since there is no output change. So I'll then in the next step I have this one register out here, right? Now I push that register here, okay, for execution, G2. Now G2, right, this is making a transition. Obviously this has also made a transition, so this is going to change 0 to 1, right? Is this going to drive, is it there is an output change there, right? Since it's an output, whether it is making a change here or not, that is immaterial. Since there is an output change, I'll put G4 here, right? Okay, now I take G4 here, right, and then I will compute whether the G4 is have to make a change or not. So G4 is going to, and since it's a, so this is a final output is available here. So this is how this event driven simulator works. Okay, I will have a netlist. Once the moment I give some input changes, right, so it will hold these previous values. Okay, so once the input changes, so those gates in which these inputs are being fed, they will be put into a register, and one of them will be whatever is put first, that will be pulled out, and then you see whether that is going to affect some other gate or not, and then slowly you will keep running this till all the events. So this is how this particular event driven simulation algorithm works. So it is much faster. Okay, now you can consider this only, we are talking about only 3 gates, but if you talk about a very big circuit, then maybe 80% of the circuit is may not be getting activated at all because of certain input test vectors. That is, so if you run a code compiler, it will run the entire program and recalculate the output at each nodes, right? Whereas this will be much faster. Okay, the another advantage of event driven simulation is we can incorporate delays also. So this is like incorporating nominal delay, like for example, for each of them, right, you have some delays for each gates, they have been incorporated, right? So what it does, now suppose I am making a change at B, so that also now I have to specify B is changing to 1, right, at time is equal to 0. So you have to specify, okay, at time is equal to 0. Now that is in the first FIFO register, right, and that is pulled here. Now B changing 1, okay, will cause a output here, a G1 output, because this is a delay has been specified now 8 nanosecond. So at 8 nanosecond this will make a change. Okay, now then I take that, because there is now only one data available in the FIFO register. I pull it here. G1 is now changing. Now from here, from G1 it is come at 8. G3 8 plus 4 is 12, and here also it's going to make a change. So it is 8 plus 8 is 16. So this is 12. So I write the 12 on top out here. Right, so this is here when my it is not first in first out, the moment this is to be put now here in these registers based on the timing, what is going to get completed faster. So that will be written on the top out here. So here it is not an FIFO kind of thing, it is the timing based here. Now 12. So I'll next I pull this 12 from here, right, G3, and I try to execute that. This is 4, so this is going to be 16, right? So I put that 8 plus where is it? We talked about this G3, right, and there is an 6, right? So G4 will be at 18. Okay, so that 12 plus 6, 18. But at 16 this is going to change. This is there from the previous. So this from the bottom, now it has come onto the top. Now I pull that out, right? So and then I execute that, and this once this is done, I have a G4, right? Now if you will find that G4, right, also has got two different changes which is happening at the input. So this will be pulled first, and then again this is done, and this will be done here. So if you see here the output, okay, G4 is actually going to 1, and then it will come to 0 like this. So is this an erroneous output? Is there a problem with this thing? Because if I see the logical thing, right, it should be 0 only, but it is going to a 1 and coming to 0. So is the issue with testing, or issue is something else? Anybody?
Issue with timing delay,
Yes.
timing to a gate.
Correct. So testing is perfect. Okay, there is no issue with this logic which we are following. Okay, there is a problem with actual what we have implemented here, and because of this particular testing, we are able to find that there is an issue in the circuit. Correct. By doing a timing analysis, we are finding out that okay, there is an issue with the circuit. This kind of a glitch will come in the circuit. So this particular code, once we run, right, in the event driven simulation, once we incorporate the delay also of the gates also, right, then we are able to find out if the circuit will behave, okay, if the output is glitchy, that kind of, or it is whether it is meeting the timing requirements, or it is causing such hazards, that can be found out. Okay, so this is, you can say this is a good method of testing, right? It is not a problem here. It is identification. There is a problem exists with this circuit, and I am able to identify that. Okay, that is what this says. Okay, so this is known as event driven. But even event driven simulation has got an issue, small issue, right? Suppose for example this is an NOR gate, right? This is changing at from 1 to 0. This is changing at 1 to 0 at the same time. Okay, because this is coming from here somewhere it's coming. Suppose let's not bother about what is here. If both the inputs are changing at 1 to 0, in a practical circuit, it is possible that because one of them will be 1, and this is changing from 0 to 1 at the same time, this is changing from 1 to 0. Okay, so practically when I fabricate it, it is possible that it remains 0 only, isn't it? Yeah, Jason, in agreement? Once I fabricate, because
Yes, sir.
what is like my testing should resemble the fabricated product as close as possible. So it is possible that in this circuit, if the inputs are coming at the same time, right, the output will remain 0. Okay. Now when I am doing this event driven simulation, okay, now both these are coming at the same time, but it will what it does, it will implement one first and then the other. Right, that's how this algorithm works. Now in one case, okay, it is incorporating, it is first doing this change. Okay, so this is 1 here, it is making 0 to 1 here, so this is remaining 0, and then this is making 1 to 0. So in this case there is no problem. But suppose this both have come together. Now this particular algorithm doesn't prioritize. Okay, it will because both are coming at the same time. It can pick this also first, execute this and do the execution later. So if it's doing the other way around, if it's trying to do, okay, this is a 0 here, it is making this also 0 first. So 0 0 will push it as to 1. Okay, it will push to 1 and then again it will come back to 0. Right. So this has gotten a small issue, not a very big issue, but it's a small issue, right? When there are when exactly two signals are coming to a gate at the exact same time, okay, then this event driven simulation, there is no provision, automatically it doesn't give any priority to the signal, right? So this is to be on priority, this is to be priority. It will just randomly pick one of them. And in such cases, there is a possibility that it might push out some glitch which may not be there in the actual circuit. Okay, because this particular software, the way this algorithm runs, okay, it does not simulate two conditions simultaneously. Okay, one each. It's an event driven, so one event at any given time it will try to resolve the output. Okay, so it doesn't like these two, it won't calculate the value of G4, right, because the algorithm has been designed for 0 1 and 1 0. It will keep killing from this register, it will keep taking one event at any given time and move forward. So that is the small limitation of this event driven simulation, right? So that's all for today. What I am thinking